The first module in digital design and computer organization is Introduction to the Digital Design, in which we are studying these topics, that is binary logic, theorems and properties of Boolean algebra, Boolean functions, digital logic gates, introduction, the map method, four variable map, don't care conditions, NAND and NOR implementation, other hardware description language, that is Verilog model of a simple circuit. In this, the very first topic is the binary logic. So let us see what is this binary logic is. So the binary logic deals with variables that take on two discrete values and with operations that assume logical meaning. So the two values the variable assume may be called by different names, that is true and false, yes and no, etc. But here, for our convenience, we are going to think that in terms of bits and assign the values, that is 1 and 0. Then coming to the definition of the binary logic. So the binary logic consists of binary variables and a set of logical operations. The variables are designated by letters of the alphabet, that may be in uppercase or the lowercase, that is for example ABC or XYZ, with each variable having two and only two distinct possible values, that is 1 and 0. So that means that a value associated with any alphabet, that can be either 0 or it can be 1. And there are three basic logical operations, that are AND, OR and NOT. And each operation produces a binary result that is denoted by Z. So which you can see here. So the first logical operation we are going to study is AND. And this operation is represented by a dot. So you can see it here, a dot operation, or by the absence of any operator, so that we can just continuously write like this without any operator. So we can represent it, that is for example x dot y is equals to z or xy is equals to z. And how to read this is x and y, that is equals to z. And the logical operation AND is interpreted to mean that z is equals to 1 if and only if x is equals to 1 and y is equals to 1. Otherwise it is 0. That means if any of the value, that can be either x is equals to 0 or y is equals to 0, or in case of both x and y are equals to 0, so the value of z will be equals to 0. Then moving to the next logical operation, that is OR. So this operation is represented by a plus symbol. Here we have given that x plus y is equals to z, and we have to read it as x or y is equals to z. And we can see the value of the z here. So z is equals to 1 if x is equals to 1 or if y is equals to 1. That means if any one of the x is equals to 1 or y is equals to 1, the z is equals to 1. And if both x and y are 1, then also z is equals to 1. So z is equals to 0 if and only if both x and y is equals to 0. Then coming to the next operation, that is the NOT operation. So this operation is represented by a over bar. You can see here, that is x bar is equals to z. So how to read it is not x is equals to z. So which means that z is what x is not. And so we can say that if x is equals to 1, then z is equals to 0, and when x is equals to 0, z is equals to 1. And this NOT operation is also referred to as the complement operation, because it changes a 1 to a 0 and a 0 to a 1, that is the result of complementing 1 is 0 and vice versa. And this binary logic resembles binary arithmetic, and the operation and nor have similarities to multiplication and addition. But in fact, the symbol used here are same those we can use in Yaudu multiplication and addition. But binary logic should not be confused with binary arithmetic. Why? Because in the binary arithmetic, when we add the two numbers, that is 1 plus 1, that is equals to 10, that is nothing but, so whose value is equals to 2, but 2 is represented in binary is 10. And but in the logic, when we write 1 plus 1 is equals to 1, and this is the OR operation, and this will be equals to 1. So here we should not get confused with the binary logic and the binary arithmetic. Both are different, but the symbols may resemble same. Now, for each combination of the values of x and y, there is a value of z that is specified by the definition of the logical operation, and the definitions of logical operations are listed in the truth tables. So you can see here the truth tables has been listed for all the three logic operations, that is and, or, and not. And this truth table is a table of all possible combinations of the variables, showing the relation between the values that the variables may take and the result of the operation. So here the truth table for the operation and nor with variables x and y are obtained by listing all the possible values that the variables may have when combined in pairs, that is different combinations 0 0 0 1 1 0 1 1, like this the different combinations with the two variables, and for each combination the result of the operation is listed in a separate row. So we can see here the truth table here. So you can see here, so this AND operation we will get 0 whenever either x is 0 or y is 0 or both x or y is equals to 0, and the z value will be equals to 1 if and only if both x and y are 1. Similar to OR operation, so whenever we are having both the zeros x and y, then only the OR operation results in 0, otherwise the result is 1. And we can see here the complement of x, that is if it is 0 its not is 1, and if it is 1 its not is 0. So now coming to the logical gates. So the logical gates are electronic circuits that operate on one or more input signal to produce an output signal. So the electric signals such as voltages or currents exist as analog signals having the values over a given continuous range, that is from 0 to 3, as you can see in the diagram. But in a digital system, these voltages are interpreted to be either of two recognizable values, that is 0 or 1. And the voltage operated logical circuits respond to two separate voltage levels that represents a binary variable equals to the logic 1 or logic 0, you can see here. So that is logic 0 and logic 1. So for example, a particular digital system may define logic 0 as an input equals to 0 volt and logic 1 as a signal equals to 3 volts. So you can see the volts here, 0 volts and the 3 volts. So this figure represents the input terminals of digital circuits accept binary signals with the allowable range and respond at the output terminals with binary signals that fall within the specified range. The intermediate region, so you can see here the intermediate region, that is between the allowed regions, is crossed only during a state transmission. So any desired information for computing or controlling can be operated by passing a binary signals through various combination of logic gates, and with each signal is representing a particular binary variable. When the physical signal in a particular range, it is interpreted to be either 0 or 1, as you can see here. So the signal range for logic 1 and this is the signal range for logic 0, and the transition occurs between these two lines, that is for voltage 0 and for voltage 3. So then coming to the graphic symbols that is used to design the 3 types of gates are given in this diagram. So you can see here, so this is the symbol for digital logic circuits. So these gates are blocks of hardware that produce the equivalent logic 1 or logic 0 signals if input logic requirements are satisfied. You can see here, by giving the x and y values, we can get the required z value that is based on the gate we are going to implement. And the input signal x and y in the AND OR gate may exist in one of 4 possible states. What are those states? We already seen in the truth table, that is 0 0, 0 1, 1 0 or 1 1. And here these input signals are shown together with the corresponding output signal for each gate. And the timing diagram illustrates the idealized response of each gate to the 4 input signal combinations. So you can see here the timing diagram, and here the horizontal axis of the timing diagram represents time and the vertical axis allows the signal as it changes between the 2 possible voltage levels. In reality, the transmission between logical values occur very quickly and not instantaneously. So the low level represents the logic 0, you can see here. So the low levels are logic 0, and at the same time the high level will be represented by 1. The AND gate responds with the logic 1 output signal when both input signals are logic 1, and the OR gate responds with the logic 1 output signal if any input signal is logic 1. So you can see here, so x and y values has been precisely mentioned here. We know that in the AND gate, so whenever both are 0, it is 0. Whenever 1 0, it is 0. So you can see here, for 1 and 1 it is 1, and for the combination of 0 and 1 again it is 0, and the combination of 0 and 0 it is 0. Similarly for the OR operation, 0 0 is a 0, 1 0 is a 1, 1 1 is a 1, 0 1 is a 1, and 0 0 is a 0. And you can see the NOT, that is complement of x. So if it is low, it is high. Whenever it is high, it is low, and whenever it is low, it is high, that is the value 1. So this is the timing diagram, so which is going to represent the logical value, that is high level, and the low level for the given input symbol. So then coming to the last point here, that is gate with the multiple inputs. So AND and OR gate may have more than 2 inputs. It get more than 2 inputs, not only 2 inputs. An AND gate with the 3 inputs and an OR gate with 4 input has been shown in this diagram. So the 3 input AND gate responds with logic 1 output if all the 3 inputs are logic 1. That is, if all the 3 are 1, then only the F value is equals to 1, otherwise it is 0. And the output produces logic 0 if any input signal is logic 0. So any one is 0 means, so the output will be 0. In the similar way, the 4 input OR gate responds with the logic 1 if any of its logic is 1. If any one is either A, B, C or D, if anyone's logic value is 1, then we will get G is equals to 1. If all the input here, that is A, B, C, D is equals to 0, then only we will getting the logic value of G is equals to 0. So these are the concepts about basic logic.